Okay, we will be waiting for like 3-4 minutes and I'll let everyone join.
Uh, Today, can you also help us with a few questions from last week? Actually, there has been a lot of problems with the questions in the last assignment. I'm not getting able the correct answers for that. So maybe if you can help us today with the solution, it may take just 10 minutes, maybe just to solve it through and come to conclusion whether it is right or wrong.
Okay, sure.
Yeah.
So I had actually wanted to show like because this week the content is pretty easy to say, like they're
Mhm.
mostly not that much. So I was thinking if I can show some demo of the like how to write the actual code. Otherwise, we
Yeah, I
can
mean,
go
that is
like
also fine. That is also fine. I mean, anyways, I mean, we can go through the slides that we have prepared, maybe, or I'm okay with if you can show me some real time code, and maybe just help solve the last week problems. I mean, it's not for the assignment marks, but more of just to understand, to have that understanding, so that we don't get wrong going forward, right? Yeah.
okay. So yeah, so I think it is fine. So we can.
I think we can start now. Yes, yeah.
Okay, I think we can start. So yeah, so hello again. So this is the week 7 of the NPTEL course in Natural Language Processing. The course instructor is Professor Pawan Goyal. This course is being conducted by Indian Institute of Technology Kharagpur, and I am Punyajoy Saha. I will be the teaching assistant for this course. Now today, in this week, we will be primarily focusing on semantics and a more finer version of it, like the computational semantics. And here we will try to find or automate the process of constructing and reasoning with the meaning of any representation. Here also there are different categories like formal and distributional. So we will mostly focus on the distributional semantics part. So which is the study of statistical patterns of human word usage to extract the mean. So we will look at, so in very simple terms, we'll look at a bunch of sentences and try to figure out what a particular word means. And those algorithms are mostly like trying to formalize this idea of construct the meaning based on the statistical patterns of human word usage. Okay, brief overview about what we are going to cover. Now we are going to move to the questions. Yeah, so this is the first question. Um, Actually, the following algorithm can learn word representation directly from the word co-occurrence matrix without access to the raw text corpus. So, does anyone of you know the answer?
I think it's number three, maybe cloud.
Yeah. What about PCA and SVD?
Mm, not very sure about it. The few lectures I've not covered yet, so I'm not very sure.
Yeah. So PCA and SVD are if you so these SVD means single value decomposition. So it is directly based on the co-occurrence matrix. So I think you need just to know that.
Mm,
So these things and CBOW we can have to use the corpus to get the context of both sides.
yeah.
1, 2, 3 will be so PCA is just a modified version of SVD.
Mm,
These things.
mm.
3 can have so these are originally defined for matrices only, SPC and SVD. So uh, it tries to compress some higher dimensions to lower dimensions. So that is the function. And for
And what
glove,
about
we already know.
what to wake is also very similar to this glove, right? It also does the similar thing, right? Or it is also based on the corpus that you use.
What to wake models are this as CBOW. So there are different versions. So glove vectors are a variation of what to wake or what to wake models, but they do not use directly the um, context. But
Hmm.
CBOW and skipgram, these two actually use the context of the word to predict the word's meaning. So that,
Okay. Okay.
yeah. Next question. So does anyone have any doubts over this? Today we'll
Yeah,
be
so basically, hot text corpus, can you just elaborate a little, please?
which one?
Now, why are we getting that? The answer is based on the key thing here, as I understand, is raw text corpus, right?
Hmm.
So, how are we looking at it, is what I'm trying to say.
No, it's without the access to raw text.
Without the access to the raw text. So if you do not have the raw text corpus but have the co-occurrence matrix, what co-occurrence matrix? Which of the following algorithms can work without the raw text corpus?
So, basically, what it means is we have that matrix. So,
Yeah, we
based
have
on
the
the
directly
matrix
the
alone,
co-occurrence matrix. So the co-occurrence
okay.
matrix in like before that it should be generated from a text corpus. That is necessary. But for this
Huh.
case, we are directly using the co-occurrence matrix. So that is the question.
Okay. So, what it means is in SIBO, we basically have those sentences,
Yeah. So
and the next step being the
in we need the left and right context of a word in the
right.
formula. So that is like how it is done. But for the others, even just the course matrix will do to calculate the embeddings or representations.
Okay, so it is basically step two. So essentially, without raw text, this can't be built. So that's where I was confused. So
Yeah.
what it means is after a stage of refinement, we don't need that. Okay.
Yes. Yes.
So basically, if I'm correct, the CBOW, the two variants of word to vex, CBOW and skipgram. So they only consider the immediate neighbors, I believe, right? And that's why they, without access to the raw text, raw corpus, you may not be able to learn the exact representation of words, right? And maybe in the glove, it's like the complete, it understands with respect to the whole corpus. And that's why if you have that representation, you don't need access to the corpus anymore. Am I correct?
Yeah. Now in CBOW, actually you need the like you don't need only the co-occurrence but also the whole context the word belongs. So I can show one example. Sure. So I think I'll come to that in a bit, but yeah.
Yeah.
Okay. So yeah, so okay. Moving to the next one. So you have to calculate the PMI for W1 and W2. So and we are given the frequency of C W1, like number of documents WI has appeared in, WI comma J is number of documents where both words have appeared in, and you have to calculate the PMI for W1 comma W2. So what is the formula for this?
PMI is, I think, log of P corpus of PW1 and W2 and divide by P corpus W1, W2.
Yeah.
Right?
So yeah. So here one thing to notice is what log to use. So if you see the question or in some questions it might be mentioned what is the log that should be used, like the base of the log. But
Mhm.
ideally, if there is nothing, then you can try with both of them and select whichever the answer is closest to.
Mhm.
So that can be one error that can come. So here, like for example, here we are using the log part. So
Mhm.
uh, we are using the natural logarithm,
Mhm.
and then we break down the formula into this. So one n is getting cancelled. So this is the final formula if we write in terms of frequency.
Yeah, yeah, yeah. So and if we knew the p probability of
Then we do not need to.
yeah, I mean, in that case, this the W1 W2 that can be cancelled as well. No, fine, sorry. That's a case of
That is
infrequent.
yeah. So that this is the joint distribution. This is just multiplication of two.
Yeah.
So
Yeah.
that cannot be cancelled. Yeah, then we just multiply it. So this is the final value ln 100, which is 4.605 minutes. So this you can check once if you have any doubt.
Mhm.
But overall, this is very simple. So
Yeah.
yeah, so this is what the answer is. So does anyone have any doubts for this?
No, not really.
Okay, let's move ahead. Then we have to calculate the KL divergence to distributions P and Q. And we have been given P x is equal to x is this and Q x is equal to. So the distributions are given based on x, and we have to find the KL divergence.
Okay.
Now, KL divergence formula is this.
Yeah.
So that gives us this value. So we are just replacing the Px and Qx here. And we have to sum it over all x. So
Yeah.
x belongs to z plus. That is one integer, positive integers.
Mm-hmm.
Now simplifying this a bit. So we took the 3x up. So we are creating one term which is exactly like to the power x, one terms which has to the power x, and the other which is p of that, so that we can separate it. So that
Yeah.
becomes this. So you have a term which has log half summation of 1 by 2x, and then log 3 by 2 summation of x by 1 2x 2 by x. And this is directly, if you check the geometric distribution. Yeah, so this you can directly get from the geometric distribution. That is summation of all to the power infinity. And
How did you get the last one? Log 3 by 2 summation of x divided by 2 to the power x?
yeah, so if I simplify this, so let's look at this term. Yeah, so if I simplify this one,
Mm-hmm.
so you can write something like the summation of this is okay. So this we are just checking inside. You
Yeah.
can write log of 3 by 2 and x.
Power x, yes. Yeah.
And then you can take the x outside with the
Yeah.
power.
Yeah. Okay. Got it. Yeah.
So this you can check like so this you can directly check in Google or something. So this is a standard formula, summation
Mm-hmm.
of x by 2x
Okay.
comes out to half
Okay.
half and 3 by 2,
Okay.
and which is also shown here. So 1 to infinity will go, and this you can calculate. So this is actually like a decreasing ratio. So finally you will get a, so you may feel that when you go to infinity you can get a very high value, but since it's a decreasing ratio, like this 1 by something, it
Becomes
will
very small. Yeah. Very small value.
finite value.
So this is almost, this term is almost negligible. It's been neglected, right?
No, it is
And then,
here we are getting a 2. So here I think it is 1
mhm.
and this is 2.
Okay.
So basically if you put 1 here and 1 half, so if you put 2 here and 2 is 4. Yeah, so half plus 1 by 4, this way it will go. I think I can refer to the correct.
1 by 2x is 1, then x by 2x is 2. Okay. All right. So maybe we'll check it up. We can check it up online about this.
Okay, so this is the function. Then we have this question. So this is also simple. So what is, does anyone have any doubts about the other one?
And just need to check that standard summation, the infinite summation. This will be good. That's it.
Yeah, let me search a bit. If I find that, I will share.
Yeah.
Okay, then this is another question. So, how do you solve the word analogy part? So, the very simple formula is that the distance, or you can say the vector distance between VD and CD should be equal to VB minus VA. Right. So if these are equal in terms of vector, so then they can say they are similar or they are analogous.
Okay.
And this turns out to be this. So if you take the VC here, so this will be the formula. But here, so will 1 be the answer?
We have A, B, C, D using word vectors.
So the basic funda is this, that VD minus VC is equal to V minus VA. So this is equal, then we can say it is similar. But then it is saying, then do a dictionary lookup for VD. You think 1 should be the answer?
Not sure, sir. I have not gone through the last 2 lectures, so not sure about it.
So just think about it. So basically,
Okay.
can we
So
do a dictionary lookup for VD?
VD is a vector for D, vector representation for D.
Yeah.
So, and what is the method of solving analogous questions? Dictionary lookup for VD. We can do a dictionary lookup for VD, right?
Yeah, but here we are not storing the dictionary directly.
A dictionary lookup means maybe.
So you see that VD is now a continuous vector space, right?
Yeah.
So think about it. So when we create a word vector representation, so if we have to store all the word vectors that is coming in the space, it will be a huge memory, right?
Yeah.
So that's why we do not store it like a dictionary. So what we do instead is we perform a cosine similarity among all the words that are present, and then find the closest terms to VD. So what we will do after we get VD, that is, we have to find the D vector basically. So after we find VD vector, we then run a cosine similarity function through all the words that are there. So this can be made faster using some indexed architecture and all these things, but these are separate. But this is the standard way, that we have to go through all the words, select the words which are having the highest cosine similarity, and those words will actually represent VD, or one of those words can actually represent VD. So dictionary lookup here is like not possible due to the scale of the how many you have to store. So even if you go by the integer vectors, it will be a lot. That's why we do not do a dictionary lookup.
So okay, so I mean, dictionary lookup here means what? I mean, if suppose we wanted to store something in a dictionary, if
Yeah, so
suppose hypothetically
here,
we are storing, what will the dictionary contain? The list of.
so here they mean by dictionary that, let's say you have a 3-dimensional dictionary, so usually it's more 0.2, 0.3. So this is one VD, let's say. Now, so they are saying for this VD, you can look at a dictionary and say what is the word. Okay. But storing this way, so let's say this will be, let's say, a cat. Okay,
Hmm.
there's a word. So this they're asking is, so if you can use this dictionary to check that what is the word. But let's say the final outcome is 0.4. So for each one of these changes, you have to store a separate thing.
Hmm.
So that will become a huge memory. So for 0.3, 0.4, 0.3, you will have to store a, uh, a different outcome. So if I have, like, I am considering here fractions. So if I consider only integers, so let's say n integers, that will become n cube, n to the power cube outcomes. You see the n, if the n is like very huge, and then you will already see that it is taking up more space.
Okay.
But in
So
this case,
what is linear, sir? So basically, if it's for each word, we are instead of storing a one-out vector, we are storing a real valued
yeah, so we are storing a
list.
real value.
Uh-huh.
But that is not the
So
main point. I am saying we cannot store it like a dictionary because it will be a huge memory space.
so in the dictionary, what it means is the key is the word and the value is the
Or
that list.
the opposite
E
of
is
this,
the value.
the value. So we have to
Huh.
get the word for each one of them. So here, so A is to B, to C is to D. We have to find D here and find D. So D we have to find. So one way could be get the VD, that is using this formula. VD is equal to BC plus VB minus GA, and then uh, look for it in the dictionary. But if you see, the dictionary will become very large, and it might be possible that we are not getting the exact match also.
Okay, and when you're talking about the n, you are talking about the number of words essentially, right?
I'm saying n can be, yeah, n is the space that we're given. So not only the number of words, so, so n can be, so I'm considering here x, let's say a
Space dimension, right?
xyz plane, xyz plane, and we are considering only the positive integers till n. So n can be 1000, for example. That is
It's
our
essentially the
entire,
dimension.
yeah, that is our entire vector space that we're getting. So
Okay, the
now,
dimension. Got it.
yeah, so now you can see that the dimensionality is huge for just representing these words. So that's why we use this cosine similar to get the closest term. So we are not saying that this vector is directly representing this word, but we are saying these are closest to that, and they have probably the similar meaning. And it can happen that VD is something else, but in our vocabulary, these are the closest words.
Okay, got it. So essentially, it is an exact match versus something which is close, right?
Exactly. But the exact match we cannot do here.
Right.
Okay. So next is, yeah, what is used by the, yeah, this is what the question was. So what is used by the CBOW model during its trading process?
Target word, output context in the left and right of the target word. Input is the target word. No, input is the previous and the next was the target word. K context on the left and right of the target word. Output the target. I think number 4.
Okay, context was on the left and right of the target word and the target word. Anyone else?
Can you please elaborate this? Because SIBO versus skipgram, one of them comes for the neighboring words and the other is the other way around, right? It flips actually.
So CBOW is like in all the related inputs, right? And then we find the corresponding target matching word to that. So I think it should, yeah. So I think either two of, I mean, the previous and next word, the target word, the previous and the next word, the target word, output is the target word. No, I think 4, sir. Most probably 4, yeah.
Yeah, so CBOW, yeah, so you're right. So scriptgram is the opposite of the CBOW. So CBOW, it takes the context and then predicts the output. So yeah. Yeah, this is the main like idea behind CBOW. So we are having the context, we have to predict the module words. So actually, this idea of like doing this way like we have the context of the surrounding words and we have to create some middle word is also used in the modern transformers. So those also use a similar idea that we have the context word, we have to predict some words in the middle. And S4 is the correct answer here.
Number 3 would have been for skipgram, right? The target word is input and the
Target word
um,
number.
so in this anyone would fit for skipgram. Input is the skipgram. What does it say?
Yeah, I think one fits for script. Yeah.
Yeah,
Well,
one fits.
skipgram. What is one? Input is the target word, yes, and the output is the context word, yeah.
Context words are the now at the output layers. The one is fit for the script graph.
Okay. Now question 6, what happens to the cosine similarity between two vectors if the angle between them increases? If angle increases, the cosine similarity and the similarity decreases, right?
Yeah,
Basically.
exactly.
I mean, it's cos of theta. The cos theta, if the lesser the value, the cos theta is 0, that means it is exactly the same, right?
Exactly.
I
Then
mean, I just had one follow-up question in this. Why we could have also taken sign similarity, right? In that case, it would have been the opposite, right? Is it? So let's say sine 0 is cos 0 is 0, cos theta is 0 is means cos 0 is 1, right? So in that case, what happens is in case when we take out cos value of any angle, the lower the angle becomes, the higher the value the output is. So cos 0 is 1 in case, right?
cos 0 is 1, yes.
Yeah. So that means when the angle between two vectors is 0, they are similar. That is why we take cos. Now, let's say we have taken sine. If we have taken sine, then sine 0 is sine 0 is.
Yeah, so that is correct, but we cannot take sine exactly. Uh, so if you know vector calculus, so the
Yeah.
basic idea of cosine similarity or any this dot product is to take the
Mhm.
projection of one vector on another.
Yeah.
So if I'm not sure if I can draw it. If I have a vector like this, and we have to, so we have to, and this is another vector.
Mm.
Now you have to take the this vector
Yeah.
and project it on this vector.
Yeah.
So that angle, so this angle, if it is theta,
Mm.
always just get a cos theta.
Yeah. Yeah.
That is the idea behind the dot product. So you cannot like use sine.
Because it's the perpendicular.
Yeah, this will be the sine theta part. That will
Mm.
not be the projection.
Mm-hmm.
So that's why.
Okay. Okay. I got it.
So idea is that we have to take the projection of this vector on the base vector or the b vector.
Because from your diagram, it seems that if we are taking the projection on the other vector, the projection can be found by the perpendicular and the and the base.
Yeah,
But
so
in the case
that
of sine theta, it becomes base and perpendicular.
so that's why we
No,
have
sorry,
the
hypotenuse
cross
and
product for
perpendicular.
this. The cross
Yeah.
product is used for that.
Uh-huh.
But that is not necessarily like a the cross product is not a scalar value. So this is a scalar value because this is on the
Okay.
same vector line.
Yeah.
Okay, so next is this. Which of the following are correct expressions for cosine similarity between what vectors of W and W?
Unit vector of the direction, length of cos theta. Sorry,
So angle between is already given. So one answer is cos phi already.
cos phi. I
What
think
is
we
the other option?
length of words vector length is LU. Word vector for WB is till day of V.
So this is
This is
length. Length is not what we are looking for, right?
yeah.
So this is not. Cos of this is not. So we have to define the. So we are already getting the cos theta from here. So this is not
Mhm.
the case. So this is another case that is there.
The cos of theta is this value, right? UV. Yeah.
U to the power t. So one thing that to notice here, it is the unit vector.
Yeah.
So
So the,
the cosine similarity does not tell anything about what is the length or length of the vector. So
yeah.
we are
Yeah.
only interested in the direction. So if we change v to also like our unit direction or unit vector in the direction, then also we are good. So we
Yeah.
not need the length for this.
Yeah.
So this is the value. Okay, the last question. So in CBOW or skipgram, what is the range of values used for hidden dimension D compared to vocal verse HV? There's also a very logical question like, so these vectors are anyway like continuous space presentations. So for a 100K size, we can do away with D less than 300. So, so D is basically the number of, so
Context.
yeah, if we have, no, not the context. So if we, so how many vector space we have? So as I said, cat, let's say is equal to 0 0.3, 0.4, 0.4, 0.5. So this 3, so this D is equal to 3.
Yeah.
So that is the hidden dimensions.
So these are the contexts only, right? These are the dimensions. I mean, the context that corresponding to which we are creating these row vectors, right?
So
And cat is the target word.
you call it as a context?
Uh, I mean, I'm referring to the DSM models. I mean, dimension semantics. Yeah, in that case.
Yeah, in that case, it is fine. In general, these are just the like the latent vectors or dimensions which represent one word. So
Hmm.
ideally, we do not have the information, but ideally each direction it is thought of like each direction should represent one particular value, one
Hmm.
particular idea. So let's say for cat, we can say it has, so if it is an animal, so this first direction, let's say, shows that it is an animal.
Hmm.
It does not happen exactly, but I am saying
Hmm.
these each of the directions can mean one different value.
Hmm. Okay, I've not actually gone through that lecture, so I'll not be commenting too many. But I mean, so this is different from how we create the metrics or the vectors in case of distribution semantics, right? Because in that case, is the dimensions are our actual words. I mean, the context words, and then
Yeah,
we
yeah,
define,
yeah,
yeah,
yeah.
define the word that how in each dimension how likelihood the word is towards that, and then we do the comparison and struggle similarity. But in this case, I believe it is what you're talking about is different than what was there in the DSM model.
Yeah, exactly. Yes.
Yeah, yeah,
So if you see, the one hot vector is a very simplified version of this.
yeah.
So
Okay,
that
yeah.
directly tells. So one hot vector is something like this, right? So zero.
Zero. Every word is every word is one dimension, and so we have only one.
So it directly tells you that if there is a one in the second column, then it is a cat. But
Yeah.
when we are compressing it, so we are looking at more fine-grained features or
Mhm.
features or qualities that can define
Mhm.
a cat. So you can think it like that. So this is just an analogy. This does not have any like real life implications, but
Yeah.
you can think
Okay.
like that. So what this vectors actually represent.
Mm-hmm. Okay.
Okay, so now we are
Yeah,
more or
in
less.
case of one out vector, basically this capital V will be equal to the size, right? So it is not D. So D is basically reducing the dimension,
Yeah, yeah.
whereas
D
in the
will be.
case of one out vector, it will be as big as V.
Yeah, exactly.
Yeah.
Yeah,
Yeah.
But I'm saying, so yeah, that is true. But what I'm saying is, in that case, you have a column defined as cat, and if you keep it as one, it will be representing cat. But when we are seeing like a word embedding, so here would be like this, something like this or this. This will represent more like latent dimensions of a cat. It says like it is 4% animal or something like that. So this is the way to think about it. Like, what does this represent? So there are now papers which tries to find out what are these hidden dimensions actually represent in the word vectors, and those are very interesting. So yeah.
correct. So it's like a vector shown in the three-dimensional space. This way.
For this, it is three dimensional, but usually like for like practical purpose, we use like t is equal to 300 or 200 to represent a space for around 100 keywords.
The interesting thing would be to understand how these values are populated. I mean, let's say in case of 3 itself, as you mentioned, so for practicality, we can understand, okay, let's say one dimension talks about animal, one dimension talks about being a mammal or something else like that. So it tells you which category it is matching much. So I think when we are creating this real value in this escape grammar CBAO, they must have considered many aspects in which a word can be described, right? And then they may be encoding them.
But this is not actually considered, but these are actually happening automatically as we go through the trading process. So
Okay. Okay.
not exactly like manually say that this vector should represent this, but I am saying in the trading process this is automatically happening because we are trading in using that context.
Okay. Okay.
So if the context is similar, then you get similar like values in one column. So that
Okay.
is the
Okay.
idea.
Okay. Got it. Got it. Yeah.
Okay, so this marks the end of this. So again, the slides are and the videos will be uploaded here in this channel site. I think you already know that by
Yeah.
now.
Yeah.
So let us move to the more fun side of it. So I found one tutorial of this, like how to actually implement these things. So okay, let me share this tab. Yeah, can you see this tab?
Yeah.
So this will basically try to see. So we'll not look into how this is trained and all, but we will try to see how these things actually, like, what are the practical uses of this, or how does it actually work on this word analogy and all this.
Hmm.
So the first is one hot encoding. So this is a very simple thing. Yeah, sorry. So here we will try to see that. So how do you create this one hot vector in a code? So, do you all of you know Python?
Yeah. I know. At least.
Yeah, yes.
Okay, let us go through it. If you have any doubts, just let us know. So this is the NumPy library that handles most of the like math part. Then we have a sklearn library, which has different metrics or classification parts. So here we are trying to create a one-hot encoder from this two sentences. Okay, so this is our corpus, for example. So first what we need to do, we have to tokenize it. So the tokenize can be simply this. So what this does, so let us see the text.split out. So if I say text.split, so I can have different types of split. So if I say split at S, okay, it will, sorry, text 0. Yeah, so it's split at 0 at S, for example. So this split function is actually used to split the sentence in different. So for now we will use a space. That space is the default version also. The default is space. So that's why we are getting a tokenized version. But this is a very simple case. Now you may want to split using some other techniques also, as per the assignment. So this is finally getting a tokenized version. Then we store them in a single list. Then because we are using a one hot vector, we do not need like this multiple lists. So these are all the words that are present. Now you run this one hot encoder. That is a function from this sklearn.preprocessing library, and you fit this tokenized step. So fitting is actually, so here fitting does not make much sense because we are not trading anything, but we are just trying to create the one hot vectors. If you run this, Sorry. Yeah, so it will give you the vocabulary and the vocabulary range. Now, next thing is, so we have created the vocabulary actually. Now we want to convert our text into, or the words into a vector. So that will be using this value. So let us try to understand what it's doing. So one-hot encoding.transform, then we are creating np.array, and we are using the text 0.split, which will be again separating the text into words. So this will be similar to this output, this one. And then a numpy array will be, so let's see the output for this. We will see the output for this within this one. So this numpy array, when we are passing something to this one-hot encoding, so you always have to use this numpy array, because otherwise it will not take the input. So now this is the array, and if I click the shape for this, so this is 6. So we want to pass it in a different fashion, so that's why using reshape. Now if you use reshape, it will be a 2-dimensional vector with one of them being 1. Yeah, so this is the reshaped vector. So there are some problems if you directly pass the other one. I'm not sure if they resolved it or not. So you can try it once. Yeah. So one is expecting one feature. So that's why you have to pass this as a this type of matrix. And finally, if you run this, you will get a token and its vectors. So it's like an automatic, so you do not need to like code anything. So this you are directly getting, and these are the word embeddings for one-hot vector embedding, one-hot encoding. Now, what are the problems of this? So one is it is inefficient. So and we create a vector where 99% of the elements are 0. So the main problem is not, so the speed is very good. So you can just create a very, like, you not have to train anything or everything. But one problem is if you have, let's say, 100k words. Now what will happen? You have a lot of every word will have like only one value as 1, others as 0. So that means a lot of space is getting wasted for this type of presentation. And the second is let's say we are trying to so we are trying to create a one-hot vector for these values. So it says that good is as different as great and bad. So which is actually false, because great and good we know are closer to each other than great and bad. So that's why like we need a mod embeddings. Now here we already know how mod embedding is created. So yeah, now we will look at one of the famous ones like the glove embeddings. This is created using I think so. These are having 6 billion vocabulary words, or I think sightings. And this is one of the most very famous or most usable word embeddings. And here you can see, if you like see the different, I think it will take some time. Yeah, in the meantime, we can look at the original. Yeah, so this is the original page for the glove vector, and you have the code and everything. So there they have like The training is again done on the global word to word co-occurrence matrix. And this is released, I guess, in, yeah, so they have different versions. So there is Wikipedia, which is we are using. So it is directly using the Wikipedia 2014 data crawl and generating. Then there is Common Crawl, which is another one. Common Crawl again with more tokens. The 6 billion tokens means there are total number of tokens that are used in the corpus. And the vocab is size of 400,000. Then you have Common Crawl two versions. One is a bit small, 42 billion tokens. Another is 840 billion tokens. There is finally one Twitter, which is having 2 billion tweets. Here it is tweets, so you have more tokens. And this is released in 2014. Yeah, let us see if it is loaded. Okay, it is getting. Yeah, so we can do many things. Like one thing that we can definitely try is nearest neighbors. So let us try this. Like, what are the nearest neighbors to the particular word? And you can also play with the other version. So usually, I think most of the computers can handle. Like, it is better to use the 300 dimensional vectors. And that can work. Or if you want to try something more heavy, so Common Crawl 840 billion will be a good choice. So the main difference among these things will be how like how much represented they are. So for example, if you use 6 billion tokens, you might miss some of the words which are present in Common Crawl. So that is more or less the difference between these pre-trained models. But then you have different sizes, so you have to store different word embedding size. So that is the trade-off. So if you have the size
Now,
available, and so you can do that.
so, but how effective will this be in our, let's say, for example, in my current work scenario, I do a lot of classification problems, right? And so recently I've started with an LP, and that's why I thought of taking this course as well. So right now, let's say I'm doing something like a news classification. Basically, I need to classify whether the given news is relevant for me or not in my given domain. So it's a financial domain. The news needs to be a financial news, right? It can be any, let's say, few examples just to give you a bit of context. So what can be a financial news for me is something like bankruptcy, an M&A, a new issue, earnings news, something like that. Something that makes
Or
that
stock
talks.
prices, yeah.
Yeah. So in that cases, how effective will this be to use in that domain? Will this words that we're talking about, are they covering more of these are covering more of generic English words? Will they be very efficient in case of financial words in that domain?
Yeah, so common, if you just talk about like news-based classification, this Common Crawl or even I think the Wikipedia one should work because these topics or this particular aspects are already present for long back. So this is into 2014, so I think at least till that time these are all well known. But
Uh,
if you are looking for a bit more, like you want to check, for example, Bitcoin, for example.
yeah.
So that thing might not be present in this Wikipedia or this Common Crawl, or even if it is present, the
Mhm.
representation or
Mhm.
so maybe it is more used for the academic section, not for the financial
Mhm.
one. So you will
Yeah.
get a different representation, or the meaning of that might change. So
Mhm.
those things can affect, I agree,
Uh-huh.
presentation. But overall,
So
if
will
we just talk about classification, I guess that should
Mhm.
more or less work.
But these models will, if you look at these models, will not be very much effective for classification. I mean, they are more suitable to predict the upcoming word. I mean, let's say for search engines and stuff to predict what can be the next word to type, right? More often, for classifications will not be much useful to that.
No, no, this will be useful because finally, so that is a separate training session.
Hmm.
You're using the prediction part. But
Yeah.
once you are done with that, you will get a representation of the word which is, in at least in their sense, it is a good representation of that word, that vector. So you can easily use that vector to classify. So it will be a particular, it will be in a particular space in the vector space where you can use that to classify similar things. So that should work.
Okay. I mean, okay, we can, yeah, I'll discuss maybe after some time about this, maybe in the next session we have. Because let's say it's something like, let's say Apple acquires Microsoft, for example. Now, in this case, how will the word embedding for acquire help me? So acquire can come with any proper noun. So in that case, I mean, will this statement will not be able to solve my classification problem, right? So let's say I say this particular news, acquired news, is a merger acquisition news for me. Now, how does word embedding help me in that?
Yeah,
Will
that
it tell
that
me,
cannot
okay,
help. Yeah,
yeah,
that cannot help.
yeah, yeah, okay,
But in any case, like I think the acquire part, you are like that alone does not
mhm,
represent the entire context. So
yeah, yeah,
here the context will play a lot more use
exactly,
than, for example, Apple also. So Apple can be
yeah,
fruit.
fruit or a company. Yeah. So
That thing also
POS
is,
tagging would be relevant here to understand what the part of speech am I talking about, and then find the relevance, maybe context. Okay.
or for now, if you, I think if you have gone into a bit depth of NLP, you can use the modern transformer. So these models are, uh, I think, more capable of like mm, predicting
Mm.
using the context of the sentence, not only the word embedding.
Mm-hmm. This which models are this? Okay, glove.
So this is the glove model that we are talking about. So this is the Wikipedia one.
Mm-hmm.
So here we are using the 300 embedding vectors.
Mm-hmm.
Yeah, just a quick question. So, like we have word embedding giving semantic similarity, right? Essentially, so if it is Apple acquiring Microsoft,
Hmm.
how will that? Because essentially, uh, acquire is basically a verb there, right?
Yeah, I
It's
mean,
an
that's what
action that
it
is
is not
taken.
exactly a problem of semantic understanding. It's more of contextual understanding of what is happening. I mean, some kind of
Problem
action.
is
Yeah,
the issue is disambiguation. So if you
yeah.
have a particular word, so there can be different meanings for a particular word, or based on the context it's based in.
Mm.
So that's why these embeddings that we have now, that are already there, like that are already popular, they use a single embedding to create a meaning of a word. But that is does not happen in real life. So we can have, let's say, bank or Apple, which have multiple meanings based on the context they are in. So that is the second or the advanced stage of this pipelines, where we are using the context as well to predict a word embedding in a way. We are using it here also. So if you see the idea that is present beforehand also, but the final representation is always a embedding, which is an amalgamation of different meanings. But now we need to separate out the meanings for more advanced classification or more advanced analysis. So that's why we need this disambiguation, and that's why this modern transformers are there. So that we can use.
Okay. All right.
Okay, now
So,
we
what exactly do we mean by classes here? When we are classifying, we need some n number of classes. So, what are the classes that we have in mind?
that depends on what is your use case. For example, for Abhishek, yeah, Abhishek, the classes are simply financial versus non-financial. For example, you can have news versus non-news. So that depends on what application you're using your models for. So you can use your models for anything. So you can even predict if some like sentence is grammatical or not. Or so the classes depends on what exactly your task is.
Okay, got it.
Okay, now what we are doing, so this text file is not in the proper format. So we will create the embeddings out of it, and we will look at it in a bit. The embeddings will be similar to embeddings embedding the dictionary, where K is the key and V is the vector, which will be something like this: that ta is represented using this word, then comma is using this. I'm not sure how much time it will take to load this. Yeah, next we will try to use this Euclidean distance to get the smallest embedding. So we are using so for each dimension like x and y, we are calculating the difference between their particular element. So n here is the number of, so n is 300 here, so number of dimensions. That will give out dxy. So this is what is done here. And we are just using the top k element. So top k similar words we will get. Yeah, we have loaded. Yes, great.
So in this case, the x and y, so the equivalent distance between x and y will be something like off and to and end, right?
Yeah, yeah. Dx and y is will be that. Yes.
Yeah.
And then we have this. So essentially, we are creating an embedding matrix. Embedding matrix using this, and then we are just, so this is again easier in Python. So you can just subtract this, and then take the norm, and finally get the closest value. So if I do this, so we are trying to get the closest value for dot. So that's you can see these are the closest value.
Mm-hmm.
So let me. So do you want to try something else? Any other word we want to find the closest similarity with?
Say
We can
closest
try
word.
your financial words also.
Yeah, let's try. Let's try. Let's say acquire. Let's try for acquire and see what do we get.
Okay.
Mm-hmm.
Let's see, purchase is already there, so it
Yeah.
kind of understands what it is. But if you
Mm.
say Bitcoin, I'm not sure if it is existing. Yeah, they are.
Mm.
But they say these things are
Not
not very relevant, right?
not. Yeah, yeah, yeah.
That is it. And there are like links also. So this is
Something like
an error also.
something like secured notes will also not be there, or secured notes.
This is a two word, but yeah.
There's a, yeah, because secured individually which does not make sense.
Yeah.
Mm.
So these are so like bigrams are also not there. So that is another problem.
Mm.
But yeah, so if you load the other one, so I think that will take more time. So I can
Mm.
share this notebook, so I
Yeah,
can load
please.
the other ones and see what are the. So we
Yeah.
can also change the top 5 to top 10 and see
Mm-hmm.
another thing.
Okay.
I think this time we'll see more. Yeah. So you
Yeah.
can see purchase, buy, sell. So this is kind of a good representation, I'd say. So
Yeah, I mean, this representation is fine, but the only thing is, I mean, yes, what we can do is we can create training sets for the model to learn all of these words to understand and classify, maybe,
yeah.
right? So that can, in that way, it can be helpful to maybe to find synonyms, the relative synonyms of the words which can be talking about the same thing, and if they are present, we consider them as well.
Yeah.
All right. Yeah.
Next a small part about like, so we have this 300 dimensional vectors, but we cannot easily visualize that, right? So that's why
Yeah.
we need something like a PCA to represent that. So let's try to do this. So this will plot. So if you get the closest embeddings, now it will try to plot them in a uh, 2D matrix using this PCA algorithm. Let's see. Yeah. So we have the acquire part. These are the words for that acquire one, and then we have computer. So the computer nearest words to computer are represented here, and the acquires are represented here.
Mm.
Here also you see that acquire and its variations are close together,
Yeah. Yeah.
and buy sell are close together. Technology software are close together. So these are, and this you can represent like these are again in sentiment analysis on all these things. You can represent this embeddings, and you can clearly see two different clusters which are representing the positive and the negative words.
Mm.
Okay, I think this is more or less it. So I will share this. I will add this to the
Yes, please. This is very nice. Yeah.
book as well, like slides as well.
And could you maybe also send us a few interesting papers or links that you have that I can maybe refer to understand more or go in depth of this word embeddings, explore them.
Okay, I can share. So I will. Let me search for a bit, and I will upload with those particular papers and add this to the slides as well.
Yeah, that would be great.
Okay, then I think we are already over time. So
Uh, I'm so sorry, but can you help us to resolve those two queries from the previous assignment? It may just take 5 minutes.
tell me.
I have the solutions ready so that you just can go through it and just we can see if that's correct or wrong. Yeah, I'll share my screen if that's okay.
Yeah, you can share this.